Right. So again, it's a pleasure to have Sascha Keweloh from Dortmund University. So she will present incorporating prior economic knowledge into structural vector autoregressions and the interaction of the oil and stock market. So Sascha, you have 20 minutes again, and we might interrupt with questions. So thanks a lot again.
Okay, great. Thanks. So first of all, I got to say I slightly changed the title. So the title is now Uncertain Prior Economic Knowledge and Statistically Identified Structural Vector Autoregressions. So let's first start with the definition of the structural vector autoregression. So in the structural vector autoregression, we have a vector of time series, which just depends on its own past and on some reduced form shock Q. And then the second equation here models the simultaneous interaction of this system. So according to the second equation, these reduced form shocks are equal to some unknown linear combination B0 of unknown structural form shocks epsilon. And if we want to estimate the simultaneous interaction, well, then we need to first identify it, meaning we need to ensure that there exists a unique mapping from reduced form shocks back to structural form shocks. That's basically identification. And in order to ensure that this mapping really is unique, well, this requires to impose an a priori structure on the system. And there are basically two ways we can impose structure on this system. We can impose structure on the interaction on this B0 matrix, or we impose structure on the stochastic properties of the shocks epsilon. That's basically it. Now, traditional identification approaches impose structure on the interaction on this B0 matrix. So the way it basically works is we start with some prior economic knowledge, which yields short-run restrictions, sign restrictions, proxy variables, whatever, and then we impose these restrictions to ensure identification. That's the traditional identification approach. And then we have these, let's say, data-driven or statistical identification approaches. And these approaches do not impose any structure or restrictions on the interaction on this B matrix, but instead they impose structure on the stochastic properties of these structural shocks epsilon. For example, we can impose structure on the volatility process or on the independence and non-Gaussianity, and then we can just use this structure to ensure identification. And then the question which motivates this paper is the following. How do we want to deal with our prior economic knowledge when we estimate a structural vector autoregression? And the observation is that both approaches, the traditional one, but also this data-driven approach, kind of propose very extreme solutions to this question. Specifically, traditional identification approaches use prior economic knowledge on the interaction for identification. So we use our prior knowledge to get some restrictions, and then we impose the restriction to ensure identification. But if we use our prior economic knowledge for identification, this basically means there's no way to update our prior economic knowledge. If we impose the zero restriction, then we impose it, it's there. There's like no way for the data to ever yield any evidence against our imposed zero restriction. So this is kind of a very extreme approach to deal with prior economic knowledge. It's like this dogmatic approach. And if our prior economic knowledge is incorrect, well, then this dogmatic approach leads to a bias. The data-driven approach, I guess, is equally extreme, because data-driven estimators typically ignore any prior economic knowledge on the interaction, but instead just estimate the system based on some stochastic properties of the shocks. And it's really important to emphasize that these data-driven estimators ignore prior economic knowledge and not lack prior economic knowledge. And the idea is, if you don't have any prior economic knowledge on the interaction, then I would argue also the data-driven approach is worthless. Because the way it usually works is, you use your data-driven estimator and you get some impulse response functions. And then you look at your impulse response function and you say, I have prior economic knowledge. I know a monetary policy shock looks like this and that. And then you look at your impulse response function and you say, okay, this one, it looks like a monetary policy shock. It works like a monetary policy shock. This is my monetary policy shock. The point is, without this prior economic knowledge on how a monetary policy shock looks like, there's no way to attach a structural interpretation to your results. And then it's also, I'd argue, useless. So in the end, it doesn't matter if you use the traditional or data-driven approach. I would argue you always need prior economic knowledge for any application. You can only choose. Do you want to dogmatize it? or do you want to ignore it? I'd argue that's basically the choice. And in this study, I tried to explore the space in between these two extreme cases here. So what I proposed is I proposed to incorporate prior economic knowledge, meaning restrictions, using a shrinkage approach into the estimation of statistically identified SVRs. And this allows us to exploit our prior economic knowledge to increase the precision and accuracy of our estimation. So we can use our prior economic knowledge, but at the same time, it allows us to model our uncertainty in our prior economic knowledge. So the estimator shrinks towards restrictions, but these restrictions are not used for identification, and therefore the data can actually provide evidence against them. And if the data provides evidence against the restrictions, then the estimator will basically stop to shrink towards these restrictions which are not in line with the data. So this is kind of something in between the two extreme cases, and the idea is to propose a non-dogmatic approach to incorporate this prior economic knowledge. So here's how it basically works. Let's just start with some data-driven estimator, maybe based on stochastic volatility or based on independence. Maybe this is maximum likelihood or GMM, whatever. Just your preferred data-driven estimator to estimate B using the reduced form shocks. And then the proposal here basically is, well, let's just add a penalty. So if we add this penalty here, well, then this allows us to impose some restriction, Rij, on some element of the B matrix, on this Ij element. And then now your estimator can deviate from the restriction. It's fine, but you pay a price, you pay the penalty. And what happens now is basically this estimator shrinks towards our prior economic knowledge. So that's the basic idea. And here's the implementation. So first of all, the data-driven estimator. In this study, I use a GMM estimator. And the GMM estimator just minimizes the covariance, co-skewness, and co-kurtosis conditions implied by mean independent shocks. So if we assume that our shocks are mean independent, well, then this implies covariance conditions, but it also implies co-skewness conditions, and it also implies co-kurtosis conditions, and the estimator just minimizes these conditions. Is it identified? Yes. If the shocks are skewed and mean independent, then this is identified. And notice it's mean independent, so these shocks don't need to be independent. Mean independent is sufficient, meaning it's perfectly fine. If the structural shocks are driven by the same volatility process, then they're still mean independent and it's still identified if there's sufficient skewness. Without skewness, we can still use information in the forced moments, but I guess then we need independence. So that's the data-driven estimator I use, but as I said, feel free just replace it with your preferred data-driven estimator. I think this one is nice, but because it imposes very little structure on the stochastic properties of the shocks. So here's the implementation of the penalty. I just use a rich penalty. So the penalty is just the squared difference of the estimator and the restriction. So if you satisfy the restriction, then there's no penalty, but it's fine to deviate. It's fine to deviate from the restriction. Well, but then you have to pay the price, you have to pay the penalty. And the price you pay also depends on this tuning parameter lambda and on these weights here. So the tuning parameter lambda basically just governs overall how costly is it to deviate from all restrictions, and it's just chosen by cross-validation. And then each restriction has its own weight, which governs how costly is it to deviate from this specific restriction. And the weights are just adaptive weights, so they are given by this formula here. And the way it works is I first calculate a first step estimator, which is just the data-driven estimator without a penalty. And this estimator is consistent, meaning if we impose a correct restriction, then the first step estimator converges to the restriction. This term goes to 0, and therefore the weight goes to infinity, meaning the weight of correctly imposed restrictions goes to infinity, and it becomes infinitely costly to deviate from correct restrictions. But if we impose a restriction which is incorrect, well, then the first step estimator does not converge to the restriction. This term does not go to 0, the weight does not go to infinity, and it remains cheap to deviate from incorrect restrictions. And that's the basic mechanism which allows this penalized data-driven estimator to distinguish between correct and incorrect restrictions. And looking at these weights also shows the relation to traditional and purely data-driven estimators. because traditional estimators also fit into this framework, but basically traditional estimators use the restrictions as binding constraints, which just corresponds to setting this way to infinity. Then you are forced to fulfill the penalty, and that's pretty much what traditional estimators do. Set this way to infinity, and that's it. Purely data-driven estimators ignore the restrictions, ignore prior economic knowledge, meaning just set the weight to 0. So the contribution of this paper pretty much is to say, okay, these are two extreme cases, set it equal to infinity or 0, and the idea in this paper is basically let the data decide on the weight of a given restriction. There's one last thing I need to add. If we want to impose a restriction on the impact of a structural shock, well, then we need to label the shock a priori. Because if we want to, for example, impose a restriction on, let's say, the monetary policy shock, then I need to know, is the monetary policy shock the first shock, the second shock, or the third shock? Otherwise, I really don't know where to put the restriction. And usually, data-driven estimators first estimate the system and then label the shocks. But this doesn't work because I need to label the shocks a priori. Otherwise, I cannot impose a structural restriction on the shock. And the proposal in this paper is, let's just start with some initial labeled estimator or guess V bar of V0. Maybe this is a traditional estimator, maybe that's the data-driven estimator. It doesn't matter. The point is you get some B matrix, and then you need to label the shocks which correspond to this B matrix. You say, for example, for this B matrix, first shock is the monetary policy shock. And then we use this initial estimator to construct a set of unique sign permutation representatives centered around this initial estimator. And then this penalized data-driven estimator only optimizes over this set of unique sign permutation representatives centered around the first step estimator. And the idea is that this first step estimator kind of determines the labeling. And then in this set, there are no permutations. And therefore, in this set, the first shock is always the monetary policy shock. Then that's the estimator here. So I propose to use this rich SVR GMM estimator. It just minimizes the mean independencies of the shocks, and it allows to include restrictions using a rich penalty with adaptive weights. And I think it's nice because it imposes very little structure to ensure identification. Mean independence and skewness is sufficient. And it also allows to include our prior economic knowledge, meaning here restrictions, in a non-dogmatic way. Well, fine, but does it work? Here's the simulation. So I simulate a system with 4 variables and 4 shocks, and this B0 matrix. And then I estimate the system using 3 estimators. The first estimator is just a data-driven estimator without any restrictions. Second estimator is the rich estimator, which uses these restrictions, so correct restrictions. The rich estimator shrinks towards these correct restrictions, the first one. And the second rich estimator...
Sascha, you have around 5 minutes, right?
Yep.
Thank you.
The second rich estimator uses the correct restrictions and 1 additional incorrect restriction. Because in the DGP, this element here is 5, but the second rich estimator is told to shrink this element to 0. So it includes an incorrect prior economic knowledge. So here's the performance on the next slide, and you will see mean and mean squared error of all of these elements of the B matrix for all 3 estimators. So that's what you see here. Mean and mean squared error of all elements of the B matrix for the unrestricted estimator, the first rich and the second rich estimator. Let's have a look at the performance, or let's compare unrestricted and the first rich estimator. The first rich estimator only includes correct restrictions. And you can see it detects these restrictions are in line with the data, and then it shrinks towards them. And you can see it because the mean squared error is like 5 times smaller compared to the unrestricted estimation. So it really shrinks towards the restrictions. And you can see that these restrictions have a value because they lead to an increase of the performance of the unrestricted elements. Mean squared error and bias is smaller here. For this element, for example, mean squared error is like, I don't know, like 3 times smaller compared to the unrestricted estimation. So this simulation shows that the rich estimator here really allows to exploit our prior economic knowledge to get more precise estimates. Okay, but what happens if we include false restrictions? So that's this estimator here. The estimator also includes this restriction here, which is incorrect because the element in the DGP here is 5, and the estimator is told to shrink it towards 0. First of all, we can see the estimator still shrinks these correct restrictions towards 0 because, again, mean squared error is like 4 times smaller compared to the unrestricted estimation. So it shrinks towards correct restrictions, and it still has a positive impact on these coefficients here because, again, mean squared error of this element is like 2 times smaller compared to the unrestricted estimation. However, if we look at this element, we see that including false restrictions doesn't really help. It leads to a bias. The true element here is 5. The estimator is told shrink it towards 0, and this leads to a bias towards 0. It's biased towards 0. But I guess 2 things are important to note here. First of all, it does not shrink it all the way to 0. It stops at a mean of 2.7 and detects, well, probably not a 0, and stops at 2.7. That's a difference to the traditional approach, because if you use the Cholesky decomposition, this element is 0 no matter what. But the second thing, which is, I think, is more important, is that this bias decreases with the sample size. So with more and more observations, with more and more evidence against the restriction, the estimator becomes better and better in detecting that this restriction is not in line with the data, and then it stops to shrink towards it. So here's now the same simulation. Sample size increases from 100 to 500 observations. And here with 100 observations, mean is 2.7. With 500 observations, mean is 4.1. So this shows that the estimator is able, with more data, it is able to update our prior economic knowledge. We can detect and neglect incorrect restrictions. And that's the huge difference to the traditional approach, because the traditional approach will never update the 0 restrictions, no matter the sample size. And additionally, you can still see that the estimator is still able to incorporate and use correctly imposed restrictions, because it still shrinks these elements towards 0, mean squared error is smaller, and the other elements also benefit from using this prior economic knowledge. Mean squared error here is again smaller. Yeah, so I think bottom line is, I think the simulation shows it can use correct restrictions, it leads to more precise estimates. So there is a value of this prior economic knowledge beyond identification. And this non-dogmatic approach allows to use it in a non-dogmatic way, meaning in a way such that we are really able to detect and ignore incorrectly imposed restrictions. Now, I think I don't have really enough time to talk about the applications here. So if anyone has any questions, I'm really happy to just answer questions at this point.
Yeah, let's see if there is something in the chat. So, right. Yeah. So someone is maybe providing some, some reference if you want. Sascha, you can see that right on the chat. Okay, yeah. Great. So, any question, please? Right. So if there's no question again, please remember that you will have the chance also to speak to the speakers during the break. We will have 30 minutes break, so you can please write down all your question if you don't get a chance to ask them now, and so you will have more time during the break. So I'm gonna stop here, and